Have you ever, looked at a machine learning model's accuracy metric? Maybe a developer proudly shows you a dashboard boasting 85 or 90% accuracy, and you just assumed it was telling you the whole truth.
Right. It's so easy to do.
Yeah, we see a high number and naturally think, wow, this is a perfectly objective, brilliant system. Well, today's deep dive is going to prove exactly why that single shiny number can be a massive, massive illusion.
It is arguably the ultimate data science mirage, honestly. We are conditioned to think of accuracy as a simple grade on a test.
Like getting an A in school.
Exactly. A 90% means an A-, so the system must be smart, right? But when you actually lift the hood on these complex predictive models, that impressive top-line grade is, well, it's often hiding some incredibly lazy, biased behavior.
And to unpack exactly how the solution works, we've got a really fantastic set of sources today. We are looking at a batch of developer logs and architectural debates about a custom AI system built for a very specific purpose.
Predicting soccer match outcomes.
Yep, soccer. But the mission of this deep dive isn't really about sports at all. Our goal is to uncover how this AI deals with complex, seemingly redundant data to predict the absolute hardest outcome to foresee in any competitive environment, which is the draw.
A draw in soccer is notoriously elusive for algorithms. I mean, predicting a clear winner is relatively straightforward. You just look for the bigger, faster, better-funded team.
Right, usually the math there is pretty obvious.
Yeah, but predicting that two entirely different teams will perfectly neutralize each other over 90 minutes, that requires a system to understand the very specific, delicate tension of a match. It's an equilibrium state that is frankly incredibly hard to quantify.
And the system trying to quantify that tension in our sources is called NIOPP. Now, I have to laugh because whoever named this clearly just smashed a bunch of textbook terms together.
It is quite the acronym.
It really is. It stands for Neural Input-Output Probabilistic Predictor.
A bit of a mouthful.
Just a bit. But the design itself is actually really elegant because both the input, which are 14 data points or features, derived entirely from a historical data set called the Final Time Results Matrix.
Often just called the FTR in the logs.
Right, the FTR. So the input and the output, which are the predictions for win, draw, or loss, are completely probabilistic. There are no subjective scout opinions here.
None at all.
No momentum metrics, no bookmaker odds, no human bias, just pure math based on historical outcomes.
And establishing that baseline is critical for everything that follows. Because the AI only knows what is in that self-contained, strictly mathematical FTR matrix. But the real drama in these developer logs, like the central conflict of the whole experiment, is a face-off between two different versions of this AI.
Yeah, it's like a heavyweight bout. On one side, you have the heavyweight, a neural network trained on the full, robust 14-feature data set.
Right.
And on the other side, a challenger, a stripped-down, mathematically optimized 6-feature data set.
Which is really the ultimate philosophical debate in data science. Well, do you give the algorithm every single piece of data you have and trust it to find the hidden patterns? Or do you prune the data down to its most mathematically essential form so the system doesn't get confused by extra noise?
Okay, well, before we get to who actually won this face-off, I need to push back on the 14-feature model.
Go for it.
Because anyone who's taken Data Science 101 is taught a golden rule. Highly correlated features are bad.
They usually are, yeah.
Right. You don't feed an algorithm two variables that move in the exact same way. It's like putting two thermometers in the same room. It doesn't make the temperature reading twice as accurate. It just risks confusing the thermostat. So shouldn't they have removed the redundant features immediately?
In almost any other context, your instinct would be spot on. You generally want to avoid feeding a model echo chamber data. But the developer logs detail a massive realization about this specific rule.
Which will...
In the NIOPP system, these features actually have to be highly correlated. It is mathematically impossible for them not to be, because they are all birthed from the exact same parent source, that final time results matrix.
So the correlation is unavoidable. It's just a feature of the environment, not some bug in the code.
Exactly. The developers realized that the push to reduce 14 features down to 6 wasn't actually about fixing correlation. It was about eliminating something much more specific and problematic in math called linear dependence.
Linear dependence. Okay, I know what those two words mean separately. But in the context of a soccer prediction model, are you saying the data is basically tricking over itself?
Think about the possible outcomes of a soccer match for the home team.
Okay.
There are only 3 mutually exclusive events: a win, a draw, or a loss.
Right. Nothing else can happen.
So in the realm of probability, if you add the chances of all those outcomes together, they must equal exactly 1.0 or 100%.
Makes sense.
Now, the original 14-feature dataset included all of these probabilities explicitly. It spoon-fed the AI the probability of a win, the probability of a draw, and the probability of a loss.
Wait a second. If the system already knows the exact probability of a draw and a loss, it mathematically already knows the probability of a win.
Yes.
It just has to subtract the first two from 100%.
And you've just defined linear dependence. The explicit win probability is linearly dependent on the draw and loss probability.
Oh, wow. Okay.
So the 6-feature dataset, which kept features like home draw probability and home loss probability, it completely removed that explicit win probability.
Because it didn't need it.
Right. It didn't lose the information. It just forced the neural network to infer the win probability on its own implicitly because the math demands it.
I see. It's like knowing the dimensions of a triangle.
Sure.
If I tell you two of the angles are 90 degrees and 45 degrees, you don't need me to tell you the third angle is 45 degrees.
Exactly. The math is already solved.
You can deduce the entire shape just from the first two. So the 6-feature model is mathematically elegant because it stops treating the AI like a toddler. It strips away the explicit redundancy.
From a purely theoretical standpoint, the 6-feature model is a masterpiece of efficiency. It represents the absolute minimal mathematical basis required to understand the state of the match.
It's lean.
Very lean. It cuts out 57% of the features. That means the AI uses less computer memory, it trains significantly faster, and it carries a much lower theoretical risk of overfitting.
Which is the danger of an AI just memorizing its training data instead of learning how to actually predict new things, right?
Right. So on paper, the 6-feature model is the clear winner.
But hold on. If it's cutting out 57% of the data, isn't it flying partially blind? I know the math says it's elegant, but how can drastically less information result in a superior model in the real world?
That skepticism is entirely warranted, and the logs reveal that real-world application completely shattered the theoretical math here.
Because when they finally ran the test, the top-level performance numbers looked incredibly similar.
Yep.
Both the 14-feature and the 6-feature models achieved a validation accuracy hovering right around 58% to 66%, depending on how they tweak the dials.
Which perfectly aligns with the theoretical math. The math dictates that both datasets contain the exact same essential information, so they should both get roughly the same grade on the final exam.
But here's where we get back to that mirage we talked about in the intro, that accuracy metric.
Yeah.
It is flat out lying to us.
It really is.
It is completely masking a behavioral chasm between these two models, and it all comes down to class imbalance.
Let's look closely at the validation dataset they used for the final exam. They tested both models on 258 unseen matches.
Okay.
Out of those 258 samples, exactly 50%, so 129 matches, were wins for the home team.
A pretty heavy tilt.
Right. And the remaining 50% was split evenly, roughly 25% D-draws and 25% losses.
Which makes sense in the real world because home field advantage is real. The home team winning is generally the most common outcome in soccer.
True.
But you mentioned earlier that neural networks can be lazy. And the 6-feature model, despite its mathematical elegance, proved to be incredibly lazy.
Unbelievably lazy.
It achieved its high overall accuracy by taking the absolute path of least resistance. It just started defaulting to predicting W wins over and over and over again.
It achieved a massive 83.7% recall rate for predicting W wins.
Wow.
And recall, just to clarify in this context, it just means out of all the actual wins that happened, the AI successfully caught 83.7% of them.
But because it dumped almost every prediction into the win bucket, it catastrophically failed at predicting the hardest outcome.
Yes. Its recall for actual D-draws plummeted to a dismal 36.5%.
It's the classic multiple choice test scenario. You have a student who doesn't actually understand the material, but they realize that C is the most common answer on the teacher's tests.
So they just guess C.
Exactly. They get a passing grade, a high quote-unquote accuracy, just by guessing C whenever they aren't totally sure. The 6-feature model isn't actually smarter. It just figured out how to game the accuracy metric by aggressively guessing the favorite.
And that perfectly exposes the danger of looking at accuracy in a vacuum. A high overall accuracy hid a fundamentally broken prediction strategy, which brings us to the clunky, mathematically redundant 14-feature model.
The heavyweight completely triumphed here.
Yeah,
It did something fascinating. It actually sacrificed a few of those easy win predictions.
it did.
Its win recall dropped down to around 72.9%. But in exchange for missing a few obvious wins, it gained a massive structural edge in the hardest category. Its D-draw recall absolutely exploded from 36.5% all the way up to 69.8%.
It nearly doubled its ability to see a draw coming.
That's incredible.
And because it traded some correct wins for correct two draws, the top-line accuracy number stayed flat. If you were a manager just glancing at a dashboard, you would think the models were identical.
But they behave totally differently.
Right. The 14-feature model is vastly superior because it actually learned the underlying mechanics of the sport rather than just guessing C.
So we know the 14-feature model won, but I want to understand the how. Why exactly do those extra 8 features suddenly give the AI night vision for a draw?
That's a great question.
What is the heavyweight model sensing that the stripped-down 6-feature model is totally blind to?
To grasp that, we need to talk about the physical reality of a soccer match.
Yeah.
As we discussed, a draw is an equilibrium.
Right.
It happens when neither team dominates the midfield, when the historical patterns cancel each other out, and when the home field advantage is neutralized by the away team's specific tactical strengths. It is a game of tension.
Yeah, it's that feeling in the 80th minute of a 1-to-1 game where you can just tell neither team is going to break through.
Exactly. The 14 features capture that tension. While the 6-feature model stripped the data down to bare implicit probabilities, the 14-feature model kept highly granular historical metrics.
Like what?
Well, it included data points for the quality of both the home and away teams, as well as specific separate metrics for historical goals scored and goals conceded by both sides.
So even if those metrics technically overlap with the overall win probability, they provide a sort of high-resolution structure.
Think of it as a topological map of the team's relative strengths. The neural network needs that slight redundancy, that richer, higher dimensional context, to detect the subtle conditions that result in a deadlock.
That makes a lot of sense.
The mathematically elegant model was simply too sparse. It didn't have enough structural reference points to recognize when a team's defense would perfectly counter another team's offense. So, when in doubt, it just defaulted to predicting the home team would win.
And the developer logs actually bring this to life with specific match predictions. And it's fascinating to see the AI's internal logic at work here. First, they fed both models a massive mismatch. Villarreal versus Real Madrid.
A classic David and Goliath scenario. Real Madrid is heavily favored to go on the road and win.
Right. And both models, the 14-feature and the 6-feature, confidently predicted a loss for the home team, Villarreal.
Right. They both saw the overwhelming imbalance perfectly.
Then they looked at Santander versus Mallorca. Both models successfully spotted that this would end in a D-draw.
Because in that case, the probabilities for that specific match were likely so overtly balanced that even the sparse 6-feature model couldn't ignore the signal.
But then we get to the real test. A much tighter, incredibly nuanced match between Saint-Étienne and Rennes.
Oh, this is the best part.
And here, the models completely fracture. I'm looking at the outputs and the logs, and they completely disagree. The 14-feature model predicts a win for Saint-Étienne, but the 6-feature model actually guesses a D-draw. Wait a minute, I thought the 6-feature model hated draws and always biased toward wins.
And that is what makes this specific match such a beautiful illustration of algorithmic confusion.
How so?
The margins in the Saint-Étienne versus Rennes match were incredibly tight. The 6-feature model, liking those granular goal and quality metrics, gets confused by the noise of those tight probabilities. It miscalculates the tension and essentially throws its hands up, landing on a draw.
Oh, so it didn't have enough data to see the edge, but the 14-feature model did?
Yes. The 14-feature model, using that redundant but structurally rich data, perhaps zeroing in on Saint-Étienne's recent defensive quality metrics at home, or Rennes' historical inability to score on the road, it correctly identifies the underlying subtle advantage that tips the scale toward a Saint-Étienne win.
It proves that sometimes stripping away the quote-unquote noise actually strips away the necessary context. The 14-feature dataset is undeniably the superior architecture.
Undeniably.
But just handing an AI the right textbook doesn't mean it inherently knows how to study for the test. And the sources reveal that how you teach the AI matters just as much as what you teach it.
The training methodology is the final crucial variable in this experiment.
Yeah, I was looking at the training logs, and frankly, there is a lot of alphabet soup in here.
There is.
They are testing dozens of configurations for a multi-layer perceptron, or MLP, which is essentially a neural network with multiple layers of digital neurons stacked on top of each other. But they mentioned swapping out activation functions like TON versus ReLU and testing different optimizers like SGD versus Atom. Is this just developer jargon for different ways the AI's brain fires?
Pretty much, yeah. Without getting bogged down in the math, ReLU and TON are just different mathematical triggers the AI uses to pass signals from one layer of neurons to the next.
Okay.
And Atom versus Stewed are basically different pacing strategies for how the AI updates its own memory during training. They're important dials to tune, for sure, but none of those were the real game changers.
Right. The logs highlight a technique called adaptive early stopping as the major breakthrough. How did that differ from how they were training the AI before?
To appreciate adaptive early stopping, we have to look at the traditional method first, which is static training.
Okay, static training.
In static training, a neural network is just told to run for a set number of iterations. In these initial logs, the static models were told to blindly run for 3,000 training cycles. The problem is, multilayer perceptrons are highly prone to that issue we mentioned earlier, which is overfitting.
That's the memorization problem.
Exactly. If you force the AI to keep studying the exact same historical soccer matches for 3,000 cycles, it eventually stops learning general rules about soccer and just starts memorizing the specific answers to the training test.
So it's not really learning anymore.
No, it's just rote memorization. When you finally give it new unseen matches, it performs poorly because it hasn't actually learned how to generalize.
It's like forcing a kid to stare at a stack of multiplication flashcards for 10 hours straight.
Right.
Eventually, they aren't doing the math in their head anymore. They just remember that the card with the little bent corner is the one with the answer 42.
That is exactly what happens. Adaptive training, on the other hand, dynamically adjusts the learning process based on how well the AI is actually grasping the core concepts. The developers implemented a specific mechanism called early stopping with a patience of 3 intervals.
A patience of 3 intervals. Okay, let me think this through. If the system is checking the AI's work periodically, say, every 100 cycles, a patience of 3 means it's willing to wait for 300 cycles of failure before it steps in.
You've got it. The system evaluates the AI's performance on unseen validation data every 100 iterations.
Okay.
If the performance doesn't improve, or if it starts to decline, which is the telltale sign that the AI is beginning to memorize the flashcards, the system starts a countdown.
I got down to what?
Well, if there is no improvement for 3 consecutive checks, the system intervenes. First, it drops the learning rate, forcing the AI to make much smaller, finer adjustments. And if it still doesn't improve, it simply halts the training altogether.
So it acts like a strict tutor. It steps in and says, okay, pencil down. You're starting to overthink this. We're done.
And the impact of that intervention is striking. When they applied this adaptive approach to the 14-feature model, it improved the validation accuracy by over 5%, jumping from 61.24% in the static run to 66.28% in the adaptive run.
But the real victory isn't just the top-line number, right? It's what happened to the recall. It completely fixed the AI's lingering laziness.
Precisely. The static model still had a terrible recall for predicting losses, hovering around 30%. The adaptive model boosted that loss S recall to 50%.
That's a huge jump.
It is. It perfectly balanced the recall across all 3 predictions: loss, draw, and win. It proved that knowing exactly when to stop an AI from overanalyzing the past is the secret to building a truly robust prediction model for the future.
This has been a massive journey today, so let's synthesize the core takeaways here. We started by challenging a fundamental assumption in data science that you should always eliminate mathematical redundancy.
Right.
We learned that if you strip away that redundancy in the name of elegance, you might accidentally strip away the contextual tension of a system. You lose the high-resolution structure needed to predict complex, delicate equilibriums, like a draw in soccer.
And we also uncovered how top-level accuracy can be a highly deceptive metric. A model can boast a high accuracy while hiding a biased strategy as simply predicting the majority class.
And finally, we saw how adaptive training, treating the AI like a student who needs to be told when to put the flashcards away, keeps the system grounded in reality.
If we pull this out of the realm of data science and connect it to everyday life, the lesson here is vital.
Oh, absolutely.
We are constantly bombarded with highly accurate algorithms, statistics, and predictive systems, whether it's a software pitch in a business meeting, a polling model on the news, or the recommendation algorithm in your social media feed.
They're everywhere.
Whenever you are presented with that shiny accuracy number, you really need to ask yourself, what is the majority class in this environment? Is this system actually intelligent, or has it just figured out how to get a passing grade by guessing C?
It really makes you look at every statistic with a new layer of healthy skepticism. Which brings me to a final thought for you, the listener, to ponder long after this deep dive ends. We just spent this entire time dissecting how a neural network requires 14 separate granular dimensions of data and highly adaptive training guardrails, just to recognize the equilibrium of a simple 90-minute soccer game.
A completely controlled environment with rigid boundaries, a set number of players, and strict rules.
Yes, so if it takes that much structural data just to predict a soccer draw, what vast hidden dimensions of data are we completely missing when we try to predict wildly complex human behaviors?
It's a scary thought.
Think about global economics, or national elections, or social movements. We constantly try to forecast these massive events using overly simplified, mathematically elegant models. Maybe, just maybe, the messy human noise we keep trying to strip away is actually the signal we need the most.